Hello folks, and welcome to the final lecture on quantum magnetism in the CDT lecture series. Today I'm going to look at ferromagnetism. Here are some of the things I'm going to cover. So, mean field theory as applied to ferromagnetism, and then we're going to look at stoner theory as applied to metals, so itinerant ferromagnetism, and finally I'm going to look at the excitations in ferromagnets and some rules, and show you how we can use some of the equations that I showed you in the previous lectures about the relationship of fluctuations to excitations. So let's start with mean field theory. So mean field theory is a way that you can understand phenomenologically magnetic phase transitions, both ferromagnetic and antiferromagnetic phase transitions. But we're going to cover the ferromagnetic phase transition today. And the idea is that on each site you have a magnetic moment, and the effect of the interactions of the electrons can be such that the this magnetic moment feels an effective field from all its friends on other sites. So here are some other sites over here which also might have magnetic moments. If the other sites are such that the moment is aligned, then with this particular site in the lattice will feel a mean field. So the mean field in general we can write as lambda times B. Actually, I meant lambda times M, so let me just change that B to an M. So M, where M is going to be the average moment over all the other sites, so it might be the sum of Mi, if this is site Mi, summed over all the other sites. So if there's a net moment in the system, then this creates the mean field, and that then in turn creates an effective magnetic field on a given site. Okay, we call it mean field because we've averaged over all of the sites in the system. So if we look at a particular site, then if there's a mean field, it will mean that the different possible states on a particular site will have different energies, and I've illustrated this here. So if we have a field like this, then the upspin state here might have a lower energy than the downspin site. Okay. So when one includes sort of statistical mechanics then, and one has a difference in energy and a temperature, for example, it means that the probability of having a given site being in the lower energy state is higher than the higher energy state here. So I've just illustrated if you were to go through the system, you might have some moments up and some moments down, but there'd be more moments up than down if there was a mean field created by an average magnetization here. So I've illustrated this in this figure here. In fact, I've got a figure with a normal field and the mean field due to the interactions I've been talking about previously, and this is supposed to be the combination of the two. Okay, so as I said before, this mean field that one can use to approximate the interactions in the system that give rise to the magnetism to ferromagnetism, you can write in this form. So it will be the actual average moment of the system averaged over all the sites times some constant mean field parameter, and that gives you the mean field on a given site. So this is sometimes called the Weiss field. It occurs in many theories of phase transitions in other contexts as well. For example, it occurs in the van der Waals equation, where you get liquid gas phase transition. It's a mean field picture, and I've just mentioned the Weiss, and also in Landau theory of phase transitions. So this slide is just summarizing what I've just said then, that you have mean fields in all of these different examples. So the one we're going to be looking at later on is going to be Stoner theory in metals. So it's a way of including the interaction between the spins. And the key thing here is this average or mean field. That's actually an approximation, and I'll mention in a minute why it is an approximation and how it can fail. So a simple example of mean field theory is the Curie-Weiss law for ferromagnetism. So here we're thinking of a set of sites. I'm just going to draw a one-dimensional system here. Here's some sites. So each one might have a spin on it. Okay, so for simplicity, this might be spin a half system where you have two possible states, spin up and spin down. So the low energy one we'll call spin up, and that might be parallel to a field that we apply. So one can apply a field and do statistical mechanics on this two-level system for a given field and work out what the moment induced would be, because these two sites have different energies. Of course, the energy would be the moment times the field dotted together or multiplied together, because we've got spin up and spin down. So using that and statistical mechanics, one can do a two-level system and work out the magnetization one might induce with a given field, and then one can work out a susceptibility from that. Okay, and if one does that for a system in a small field, this is the susceptibility you would get. It's the Weiss susceptibility, and there'd be a temperature dependence, which comes from the effects of the thermal fluctuations on here. Obviously, at higher temperatures, if KT is much bigger than the spacing of the two levels you've got, that will tend to make the populations of the two states similar, and then as you lower the temperature, they'll tend to go into the ground state, and the susceptibility will increase, as you see from this Weiss law here. So the Weiss law is just for thinking of a single site. Actually, we just treat all the sites separately in the Weiss law. But now if we add in our mean field, so instead of an atom just seeing a field that we apply, a B field, it sees the effective field from its friends. So for example, like this. And then we can work out the average moment of its friends here, mu, and the mean field that we might get is going to be the BI, I for interactions, and that's going to be the average moment over the other atoms times some molecular field parameter here. Okay, so in the case of no interactions, then when we derived the Weiss law here, we just had the moment was the susceptibility times the field, and now we're going to add interactions, which means we add an extra field due to the interactions here. So we add a BI as is done in the last equation. So now we can substitute our susceptibility in here and work out what would happen to our interacting system as a function of temperature. So rearranging this last equation, we're going to get this equation here, in particular this one at the front here, and if we substitute in now for the temperature dependence of the susceptibility, we're going to get this equation here. which is the Curie-Weiss law actually. So now we've got a temperature dependence of the magnetic moment, or the susceptibility, if we work out the susceptibility, which would be the ratio of mu naught divided by the B here. And you can see that the susceptibility as a function of temperature goes as T minus a constant theta. So the constant, of course, would be the intercept here. And I've just noticed, in fact, that this should be chi minus 1 here. So this would be the Curie-Weiss law. And what this is telling us is that the interactions in the system that we put in the mean field is going to give us magnetic order below some temperature. So the Curie-Weiss law is a simple example of mean field theory that you may have, well, should have already seen in your undergraduate master's courses. And another example of mean field theory is actually Landau theory, which we will be using a type of Landau theory to look at metals, ferromagnetism in metals, in a minute. So Landau theory is a general theory which allows you to express the energy, the Landau free energy of a system in terms of a power series in its order parameter. So what you see here, this equation here, is an example for a magnetic system, a ferromagnet, where we've written down the Landau expansion for the Landau free energy as a function of the order parameter, which in this case is the magnetization in the case of a ferromagnet. So you can do some symmetry analysis of the system, and that can tell you which terms in the Landau theory you allowed. So in the case of a ferromagnet, then you just get the even terms, as you can see here. And the notion that's used in Landau theory to describe phase transitions is that is one of these coefficients, this one here, the A, for example, can be temperature dependent. So when you change the temperature, this shape of the curve you get plotting the magnetization, the order parameter, plotting the free energy as a function of the magnetization changes. So in the case of a ferromagnet, then at high temperatures above its ordering temperature, you would have A and B both positive, and that would give you a curve such as the brown curve here. And that would mean that the lowest energy state, the lowest free energy state, would be the state with m equals 0 here. So as you lower the temperature, then in Landau theory, this A would change sign, and you would get a curve that looks something like this purple curve. So for small values of m at lower temperatures, if A was negative, then small values of m, this would go negative, and then for larger values, the second term here would dominate and it would go up again. So in the Landau theory, the A is temperature dependent, and that allows us to predict a magnetic phase transition. So in the simplest case, you'd expect you would hypothesize that it varied linearly in temperature. So it might vary something like this. This would be A versus T. So at high temperatures it would be positive, low temperatures it would be negative, and it would cross some temperature here, which would be the ordering temperature. So what I haven't explained to you would take too much time, I think, in this lecture, is this A parameter actually is the mean field changing with temperature. So one can show that that's what phenomenologically that's what happens. Well, at least this A parameter has a component of the mean field changing with temperature. So as you go to lower temperatures, the effect of aligning the field is more beneficial, and it can lower the energy of the system. So we'll see later, usually there's two contributions here. There's something that looks like a kinetic energy which might increase when you increase the moment, and a mean field which can lower the energy of the system. And when that second term dominates, then A can change sign. So the Landau, drawing the Landau free energy versus M here illustrates another point, which is that in the case of mean field theory, you assume that the only thing that's important is the average magnetization system and average magnetization of the system, and you assume that doesn't fluctuate with time. It's just a constant. So in reality, in a system with lots of different sites, then as we've seen previously, one can get fluctuations in the moment on each site, and these are neglected, these fluctuations that one might have if you look at the time and spatial dependence of the moment. So different sites can have different moments, and a given site can have a different moment at different times. So in Landau theory, mean field theory, you're assuming basically that all the sites have the same moment, and as you go through the phase transition, they all develop a moment at the same moment, and as you go above the phase transition, the moment disappears. So that's an approximation. That's a consequence. That's called the mean field approximation, when we assume that they're all the same, and only the mean is important. So there are theories that go beyond the mean field theory and include the effect of fluctuations. So a simple phenomenological theory that does this is an extension to Landau theory called Ginzburg-Landau theory. So in Ginzburg-Landau theory, instead of considering the moment here that being uniform in the system, one can replace the moment with the average value of the moment, here say m, and a bit that fluctuates from site to site, a spatial dependent moment. And then the Landau free energy, which was previously just a function of this average, can be written as a function of the spatial dependence here. For example, this is a sort of a simple form for Ginzburg-Landau theory, where we write down the Ginzburg-Landau free energy. Okay, and we consider these three terms here. So the moment squared, and the moment to the fourth power, and this is the gradient of the moment in space. Okay, and then we have our coefficients, this time A, B, and C, and basically we integrate or average over space these different contributions to give us a free energy here. So when we go to Ginzburg-Landau theory, then, for example, if this C is positive, this last one, it means that this last term will tend to suppress variations of the moment in space. So if m of r is going like this, then obviously if there's a gradient in it in a given region, then that's going to cost energy in this situation. So the Ginzburg-Landau theory then allows you to include spatial variations in the picture beyond the mean field theory. So that raises a more general point in magnetism then. So if we just think about our magnetization, our local magnetization varying in space and time, then when we write theories in terms of this quantity, we have fluctuations in magnetization that are allowed. So this is going beyond the mean field theory. So these fluctuations can affect, when you do theories including them, they can affect the transition temperature you would predict. In fact, they tend to suppress the transition temperature in general, and the existence of fluctuations can be seen also in reality. So you get critical fluctuations when you look at the system, which wouldn't be predicted by the Landau theory. So here are two bulk properties of a ferromagnetic system going through a phase transition. So here we have the inverse susceptibility, which I had before, and on the left hand side, and on the right hand side we've got the heat capacity. So on the top panel you can see the predictions from mean field theory. So here's the prediction we had from the Curie-Weiss theory, which was a mean field theory, this straight line here, and many of you will have seen the prediction from mean field theory for the heat capacity for other systems in your undergrad. And so this is what mean field theory would give you for the ferromagnet then. So there's going to be no heat capacity above the Curie temperature here, and then there'll be a jump in the heat capacity, and then you have this variation like this. So this is without fluctuations. If one puts fluctuations into the theory, one sees that these two behaviors on the top are changed qualitatively. So if I do them backwards, then the heat capacity here has a temperature dependence above the Curie temperature. As fluctuations appear in the system, they contribute to the heat capacity because there's degrees of freedom which energy can go into, and in particular you see them in the disordered state. So this is a way of seeing critical fluctuations then. The heat capacity is a nice probe in the sense it picks up everything. So if there are some excitations, some critical fluctuations, it will pick them up. And then of course in the ordered state you again have these, it'll be a different variation to the mean field theory, but you get a cusp here actually at TC, but again it drops down as you go away from the critical point. And here in the susceptibility, you see the effect of the temperature dependence of the susceptibility is different because of the critical fluctuations. I've drawn a couple of figures here just to illustrate the effect of the fluctuations and why mean field theory doesn't work. So let's imagine we're looking at the specific heat here and warming the system up from the ordered state to the disordered state. So in the ordered state we'd have all the moments aligned, and we could work out the energy of the system. So this is the Hamiltonian we had before of a Heisenberg system. So you can, if J is negative, the Heisenberg interactions would give you ferromagnetism. So this is what you see here. Okay, and then in a mean field theory, then this would lower the energy, and then as the system lost its average magnetization, up here, then nothing would happen. But in reality, if we imagine what actually might happen in the system as it goes just above TC here, we'd probably have local regions, and I've drawn here two regions close in space, one with the spins locally all lined up, and then one here the spins are all locally pointing down. So, and the exchange interaction would tend to allow these things to happen. They would encourage nearest neighbor atoms to interact and lower the energy of the system if J was negative. So this little configuration here is something that one might get just above the Curie temperature, and it's just above because it has no average magnetic moment. So in mean field theory, this configuration would not contribute to the energy, because when we average here, there's no net moment. Whereas if we go beyond mean field theory and add up all pairs of neighbouring atoms, like this pair and this pair and this pair, would say these pairs being aligned would lower the energy, but these pairs here would also lower the energy. The only pair that doesn't do much is this pair here. So this would contribute to the energy in this region up here above Tc, and the heat capacity, as you put more and more energy in to warm the system up, it would correspond to be breaking up regions like this, where we have correlations forming in the system before we get the order. So these are like local correlations. So that's a very simple example of where mean field theory would break down. So finally, just connecting excitations and the properties of systems, then let's start at very low temperatures where we're in an ordered state. We looked at the excitations, the spin wave excitations in such a system last week, and we saw there's nice excitation spin waves in ferromagnets. And we saw that if we excited a spin wave, it lowers the magnetization. We flip the spin of the system. So an interesting thing to note is this diagram on the right, which is the magnetization versus temperature of nickel. So as we warm the system up, this first drop of the magnetization we can think of as being due to the excitation of spin waves, this first drop here. So, and in fact, if you put in the spin wave theory and the dispersion of spin waves, you can predict quantitatively what this drop is. And then if you look at the heat capacity, then this initial rise here would correspond to putting energy into the spin waves of the system. And then as you increase the temperature further, there'll be lots more excitations. The system will become agitated, and those excitations, when you approach the Curie temperature, are the critical fluctuations that one gets in a phase transition as one approaches the critical point where the phase transition takes place. Right, now let's look at the Stoner theory. So Stoner theory is an example of mean field theory, and in fact Stoner theory is based on the Hubbard model, which is a simple model to describe interactions in metals, and one of the things that can come out of the Hubbard model is ferromagnetism. So here you see the Hubbard model written down. So what have we got here? So we're thinking of different sites. We've called the sites J, and we're thinking of electrons that can go onto these sites, and in this particular version of the Hubbard model, we can have one orbital with two possible spins. So we could have a spin up and a spin down on our site. So if we have a spin up and a spin down on the same site, this second term in the Hubbard model then would give us a contribution. So we can see it's a product of the number of spin ups and the number of spin downs on the same site. So we've got site J and J up or J down. So when we have the two electrons on the same site, they have to have opposite spins because they've only one orbital of each one. And if they are on the same site, there's a Coulomb energy cost to having them there, which is denoted by the Hubbard U. Okay, so this is the Hubbard model for the interactions. And then in addition, we're going to imagine that the electrons can move through the solid and have a band structure. So this first term is the sum of the kinetic energies for our electrons in a band. So we have this is a sum in K space this time. So it's a mixed model where one term is in real space, the interaction term, and the other term is in K space. So this would be K, and this would be the energy, single particle energy, epsilon. And we're going to imagine that the two spin up and spin down states, this first term doesn't depend on the energy of the spin state. So any spin dependence is going to come from this second state. So here we've got the number of electrons in each K state and spin state in K space, and this is the single particle energy in K. Okay. So these two terms are loosely called a kinetic energy term and potential energy term. So you can see that the second term here is potential, it's interaction, and this term is mostly kinetic energy, except one has to remember that once you have a band structure that's not a parabola, if it has a band structure, if it turns over here, of course, then this turning over in the real band structure is due to the interaction of the electron with the potential of the atom. So it does have some potential energy in it as well. So if this is a real band structure, it's not strictly kinetic energy. But in this lecture we'll call this kinetic, this first term, and this is potential energy. So when one talks about magnetism in a metal, it's very convenient to think about the states in the first term. So if we quantize the system with a field along Z, for example, then we have spin up and spin down states, and so we can represent this what's happening in this first term graphically then by drawing two curves here, one for the spin up electrons and one for the spin down electrons. So when the ferromagnetic state forms, of course, we're going to have more spin ups and spin downs. So let's represent that here. So if their spin up states are occupied up to some energy, let's call it mu up, and then the spin downs here to mu down. Then we could work out the number of states occupied with the spin downs and the spin ups by integrating these areas here, if this was a density of states plot, and this difference would give us give us the magnetization of the system if we count the number of spin up electrons and the number of spin down electrons. So we'll look at that in a minute. But another interesting thing to do is to add up the energy of the system in this case. And one can show actually that if you have two bands like this and you go away from the equilibrium energy where they are there's equal number of spin ups and spins down, you'll find that the energy of the system increases as the difference in the splitting here squared, or the magnetization of the system squared. Okay, so this is what you find, that the change in energy of the system is given by this equation here. This is the number of electrons, this is the density of states, or magnetons, and then the magnetization that you get in Bohr magnetons. So redistributing repopulating them in this way, so having a different number of spin up and spin downs, will give you an increase in the kinetic energy, in the sense that I said before, that's the energy associated with this first term. So this is actually what we had in the Landau For energy, remember, we had that the lambda for energy was A times m squared. So part of the contribution here to the A is going to be this increase in kinetic energy, which comes from this term here. And that will tend to favour the system being paramagnetic, of course, because if one wants to lower the free energy of the system, and there's no tendency to align the spins, then it's better to have the populations of the up and down spins the same. So the second term here, the potential energy term of the Hubbard model with the Hubbard U, which describes the interactions between the electrons, Coulomb interactions when you have them on the same site. This is the term that's going to give us a mean field and cause the ferromagnetic transition to occur. So let's have a look at that. So one can treat the Hubbard model in a mean field limit. One can also do more sophisticated modeling on the Hubbard model, which we're not going to look at today. But if one does it in a mean field limit, then one replaces these two operators here, where we're summing the number of electrons on each site, with their average values. So the second term, that sum, just becomes the average value of this site, and then the average value of the second site, so the average number of spin up on the site times the average number down, and we've replaced the sum with an average times the number of sites, n. So this is now the mean field approximation to the Hubbard model, where we replace these two operators with their average values. And that actually gives you the basic Stoner theory for ferromagnetism if you follow that through. Okay, so we know that on a given site, then the average up and the average down is just the average number of electrons on the site, okay, which would be, say, n. Okay, and we also know that if you take the difference, the average number up times the average number down, that will, and then multiply by the number of sites, that will give you the magnetization of the material. So that's this equation here. So we've got, we can make a transform then from the n up and n down to these two variables here. One is the total number of electrons, basically, or the average per site, and then the other variable would be the magnetization. So here, this is just rewriting this equation, the energy in terms of the total number of electrons, and if you like, the spin up minus spin down. Okay, so this is now the mean field approximation of this potential term. So this is a constant. You've got a certain number of electrons in your system, but you can see that this term will lower the energy for finite magnetization. So if you start to put electrons that are all in the same up, then it will lower the energy of the system. The reason for that, you can see if you go back to this first term here. So in order to, if U is positive, which it is, then you will raise the energy if you have electrons on the same site. So you have a spin up and a spin down on the same site. It will raise the energy of the system. So one way to avoid that is if all the electrons are pointing up, then they can't be on the same site, because we're only allowed, there's only one orbital, and that will mean that we have a magnetization, and we start to lower the energy. So we can add this potential energy term to the kinetic energy term that we had before, and that's what you get here. So this is the net energy as a function of magnetization, and you can see you've got two terms that depend on the square of the magnetization. So we can take out a factor, basically, of all this stuff in front of them, and if we then look at that energy versus m, if that factor is positive, then it's going to look like this, and we'll have a power magnet. And if it's negative, it will look like this, the m squared factor, and the system will go into a ferromagnetic state. Of course, eventually this would have to come back up again, and the minimum here would determine the moment that we would get. So the condition for the ferromagnetism to occur, various things cancel out. Well, the mu b's cancel out the magnetons, and you're left with this thing here. So the condition for ferromagnetism would just be the U times the density of states is greater than 1. So that's called the Stoner criterion. If one goes through the periodic table, one can have a look at the Stoner criterion. One can calculate U, or I as it's sometimes called. That's the cost of having these two electrons on the same site, and this is what you find. It's sort of vaguely constant across here. This is atomic number on the bottom here. Okay, and then what varies a lot through the periodic table is the density of states at the Fermi energy, which is shown at the bottom here. So this range of elements here are transition metals. This is the 3D transition metals, and these are the 4D transition metals. So if one multiplies these two things together, the I and the density of states in the appropriate units, one can plot this function here. And in these units, if I times d is greater than 1, one has ferromagnetism. These are all predictions from density functional band structure theory, and you can see that it predicts that 3 elements satisfy the Stoner criterion. So iron, cobalt, and nickel in the 3D, and then palladium is in the row below, the 4D. It's close to being ferromagnetic, but it's not actually ferromagnetic. And these are the elemental ferromagnets in the 3D series. Of course, there are others as well, such as gadolinium, which is further down the periodic table and not shown on this plot. So iron and nickel are strong-ish ferromagnets, meaning that when the metals go into the ferromagnetic state, the band structure changes quite a bit, and that's illustrated here. These are some pictures from, I think, Stephen Blundell's book, where you've got the density of states against energy for the power magnets at the top and the ferromagnetics at the bottom. And you can see in the case of iron, for example, there's a sort of bit of Fermi surface here, this peak in one polarization of the spin that's not present in the other. So there will be sheets of Fermi surface that only have one spin. In nickel is a little bit weaker, so that the sheets are not so different. And here's some pictures of the Fermi surface of iron. So this is the spin down and the spin up in the Brillouin zone, and you can see the Fermi surfaces are quite different for the two spins. And here's the same thing for nickel. So this big sheet is similar in the two spins, but there are extra pockets here that you get for spin down and not for spin up. At the beginning of the course, we mentioned the wave vector dependent susceptibility. So in the Stoner criterion that we've been using, this is basically thinking about the susceptibility for a wave of 0 wave number, so a wave of infinite wavelength, so a constant in space. But you can apply the Stoner ideas to other wavelengths of order, and you can have a generalized Stoner criterion, which is this one here, where instead of chi, we have the wave vector dependent chi in the Stoner criterion. So some Fermi surfaces lead to having the maximum in the chi, the wave vector dependent chi, being away from Q equals 0, such as chromium. And this means that chromium orders with a finite wave vector. So it has a state where you have a spin density wave. So the magnetization would vary in space. And that's illustrated here schematically. So one might have the wave vector dependent susceptibility, and if at some value it comes above 1 in appropriate units, then the system will order in that case. So I'd just like to finish up by talking a bit about excitations now. So in a metal, one can have spin waves. In a ferromagnetic metal, one can have spin waves. But one also has other types of excitation. And in particular, if one has two bands, these are two bands with spin up and spin down, okay, one can excite electrons from a spin, the low energy band, whatever that is, spin up to spin down is illustrated here. So so this is an excitation where the spin has to change because there's only spin down states here, and these are spin up states here. So this is a difference that's induced because of the Hubbard interaction, making the energies of spin up and spin down different. And this is an excitation that goes between the two. So this particular excitation that I've drawn has a change in wave vector here. So we've got an initial one and a final one. So we could say Q equals, so initial minus final, delta Q for the excitation, and a change in energy. So this would be omega, also omega initial and final with these two energies. So this is a spin flip excitation, sometimes called a Stoner excitation. And this, when you work out where these are allowed, you'll find that you take your band structure and you can construct a map in the space of the excitations, the Q space of the excitations, rather than the K space of the electronic states. And this is the sort of thing you get. So this region here is where you're allowed to do these excitations. Obviously in this case you could see if you were sort of below a certain energy, you can't make it up to the top band and no excitations are possible. Okay. And then, but at lower energies you get spin wave excitations, because you remember it's very easy to get a long wavelength spin wave excitation where you locally rotate the spins. So this is the sort of generic picture of magnetic excitations in a metal. So you have spin waves down here, and then at higher energies and higher Qs you have Stoner excitations. They can't really coexist because the spin wave will couple to these excitations and decay into them. So in some materials you see the spin wave excitation disappear. It doesn't get all the way to the Brillouin zone boundary. So those are typical magnetic excitations in metals. So I'd just like to finish up with the last bit of the course now, which is quite advanced then, which is useful knowledge for many people to know, but if you're doing scattering experiments and things like that, this is sort of core stuff. And it brings together various things that we've looked at. So I'd like to just connect fluctuations and excitations in the ferromagnet. So you can do similar things to what I'm going to say in antiferromagnets and in systems in general. But let's have a look at the ferromagnet. So I showed you earlier in the course you could think about excitations of systems such as a harmonic oscillator in terms of response functions. So spin waves, the basic model you use to describe spin waves is a set of harmonic oscillators, coupled harmonic oscillators. Here is the response function actually computed for a spin wave in a Heisenberg magnet, and you can look in the book by White that I mentioned in the first lecture if you want to know about that. So this is the imaginary part of the susceptibility for a spin wave. So a spin wave in a metal then would be, well, spin wave in a ferromagnet then would go as Q squared. This is the energy, the spin wave, omega we're calling it here. And then if we think about for a particular energy here, particular Q would have a certain frequency or energy of our spin wave. And then if we were to make a cut to write a function as a function of omega going along here to describe it, then the actual imaginary part of the susceptibility would only have a finite value where the system can absorb energy for this particular wave vector here. That's what this delta function is doing here. And remember I showed you that if you plot chi double prime as a function of energy, then when it sort of peaks up, when the imaginary part peaks up, that's where you have your excitations. So these are the two excitations. So this is excitation where you where the system loses energy, and this is an excitation where it gains energy. Then this is the spin of the system. So this is the this could be the excitations in a ferromagnet. Okay. So previously I showed you the so-called fluctuation dissipation theorem then in the second lecture, and this is the fluctuation dissipation theorem in general. So you have your excitation, you have this strange Bose factor here, and from these two things you can work out the power spectrum of the fluctuations. Basically what it is telling you that if you have an excitation described by a response function, then there will be fluctuations associated with that. So we can use this, say we can take a case of a ferromagnet, we've got this chi double prime, and then it has excitations associated with it, and it has fluctuations associated with it. And the question is, how much fluctuation does it have? So we'll come back to the fluctuations in a minute, but let's just think about two quantities that are very useful in understanding order and fluctuations that one can easily understand. And these are the m squared and m as a function of position and time, as it were. So let's just look at some moments in space. So here I've just randomly drawn 3 atoms. They've all got moments on here. Okay, so I've got moments. So we can think of the question we could ask is what's the average m squared or m on an atom in some crystal. Okay, so if we just take the m first, then so we're averaging m. So I just do m. So m is an average, it's a vector in general. So if there's no order in the system, of course, then the average m would be 0. So if we had a ferromagnet and we went above Tc, then m would be 0. And then when we went into the ordered state, if we had a system where they're all nice, if we had spin a half system and all the spins lined up in the same direction, we'd get a well-defined value for our m. So if it's a spin a half system, as I just said, if all these were s equals a half, then the average moment would be a half. So we'd have, say, m a half. And the way we denote this is we choose a quantization direction z. So we could say mz was half, or sz is a half to be more precise. Let me write that down. So I'll just get rid of this thing. So if we had sz is a half. So if sz is a half, then the actual moment, of course, is going to be g s times mu b. So I'll correct that here. So mz would actually be 1 Bohr magneton for a spin a half. Okay, so this is the sort of expectation then that you would get for the average atom if we're thinking about the moment here. Okay, so this is telling you about the presence of order when you just look at the moment by like this. The other quantity then is going to be m squared or s squared. Okay, so let's have a look at that. So we're going to look at s squared now. So I've just redrawn the moments. So these are moments, s equals a half moments. So what's going to happen is these moments can point in different directions, and if they're all pointing in different directions, we don't get an average moment, but we still get a moment on all of these atoms, right? So we'd expect the average moment on the atoms then to be the quantum mechanical operator ss plus 1 when we apply it to the atoms. So on spin, if it's spin a half, this would be a half times 1 plus a half, which would be 3 over 4 for s, or if we worked out what it was in terms of Bohr magnetons, then we have to multiply this by g2 and by the Bohr magneton. So we'd find that the average moment squared would be 3 Bohr magnetons for s equals half system. So you see that written here. Okay, so so how do we measure these two things? Well, if we want to measure the moment, of course, this moment, if we're measuring some ordered moment, particular, we could do a diffraction experiment and measure the ordered moment from the Bragg peak. So we'd measure the elastic scattering and get the ordered moment. If we want to measure this this other quantity, m squared, how do we get that? So I'd just like to show you that. We can use the Parseval formula applied to this case. So this is something that comes from optics, and it means that if you integrate over the whole of your power spectrum of the fluctuations that you're looking at, so we're looking at magnetization fluctuations, and when we're doing our quantum magnetism, then our power spectrum actually is a spectrum as a function of q and omega, which you see here. So if we want to capture this this fluctuating moment squared, we have to actually integrate this over all q's, or all relevant q's, and all energies. So the relevant q's are the q's in the first Brillouin zone, and the energies are all energies from minus infinity to infinity. So that's what you have to do to get this m squared experimentally. This is predicated on the fact on assuming that you can measure this from scattering experiments such as neutron scattering or X-ray scattering. Okay, so that's what you have to do in theory. So let's see how that actually works out. So if we want to get the fluctuating moment, then if we look at the fluctuation dissipation theorem, then this is the fluctuating moment here. One can integrate this thing up, which actually corresponds to integrating this thing, the response function, in from the fluctuation dissipation theorem. So here's things get a bit complicated here, but I'm just going to tell you what happens then. So actually, if you want to do the real fluctuating moment, you have to find the fluctuations along 3 spatial directions, so the fluctuations along x, y and z, you add them up in quadrature. So then you have to add up 3 response functions, 1, 2, 3. These correspond to, say, applying a field along x and getting a moment along x and so on. So this is the integral you would have to do to get your fluctuating moment. Okay, so this is the integral you have to do to get your fluctuating moment. So now, if you do that for a ferromagnet, okay, then these excitations here are going to be the spin waves. Remember, the spin waves are the excitations, and in the case of, say, a Heisenberg ferromagnet, let's put the metals to one side for a minute, the spin waves are the true excitations, they're eigenstates. So that's an interesting example to do, and you can do that. Work out what the fluctuating moment corresponding to the spin waves would be, okay, by integrating the response function, which I'm telling you that you can compute it, and I showed you what it was. So this is one, this is the response function. Then I've just taken positive energies, and we're going to take 0 temperature, and this factor here, if you work it out, at 0 temperature, only in 0 temperature limit will only contribute on positive energies. The positive energies would correspond to the 0 point fluctuations. Okay, so we're doing all this in the quantum mechanical limit, quantum limit, the 0 temperature limit. Okay, so this is the response function, and in fact it turns out for a spin wave, because they're kind of precessions of spins that they physically, then there's only response along x and y, and the z direction, the response is actually 0, so that's here. So if you do that, you work out what it is, you can work out what the fluctuations correspond to the spin waves, and you find actually it comes out for the spinor half case then to be this quantity here. So it comes out to be g squared mu b squared. N is the number of atoms, the spin. So g is the lambda factor, so that's 4, and of course s is a half, so you're going to end up with 4 times a half, which is 2. And here's the these are the contribution of the spin waves to m squared. So if I just go back to units, the spin units, and just do the general case with spin s, then the amount of fluctuations in this m squared due to the spin waves, then let's just do it in units of spin. So we get rid of these guys. We're just left with s times n. So this is the contribution of the spin waves to the fluctuating total fluctuating moment. Okay, so here we are. That's what I told you before, the spin waves. Now, if a system's in an ordered state, then, and we're working out the expectation of s squared averaged, the actual order will also contribute to that, because they'll all be pointing in the same way. So we have to square the ordered moment as well. Okay, so then that would be on each side we'd get a value of s squared, and so the what you find is in fact that the total moment per site can be split into 2 parts. This is due to the sort of the static or the average part, and then this is due to the excitations. So just to summarize then, what have we found? Well, we're trying to think about where the moments on the different sites go, the quantum moments on the different sites in our ferromagnet, and relate them to sort of collective order and collective excitations. And what we found is that we have a spin wave that looks like this. For example, this could be Q, and energy. And then we have, if we were to do a scattering experiment, we would find somewhere there was a magnetic Bragg peak, which you could also measure. So the moment, the S times S plus 1 that we have on each site, the moment squared, we can write that as S squared plus S, basically. And this bit here is the spin wave, goes into the spin wave, and this is goes into the Bragg peak, the average moment. So these are fluctuations, and this is the order. For a ferromagnet, it's a very clear separation of the two things. So if you were to measure the spectral weight from the Bragg peak by scanning and measuring that, and you can add up this, you can then get the moment, total moment on each site. And that's summarized here. So this is a sum rule for the magnetism in a ferromagnet. Then you saw the spin waves are here, and we've got the Bragg peak. In principle, there's other types of magnetic excitation, but in the case of a Heisenberg ferromagnet, the spin waves are a good eigenstate. So both of these are kind of eigenstates of the Hamiltonian. There is no other excitation you need. In general, in a metal, that wouldn't be the case, because this the spin waves wouldn't be a good eigenstate of the Hamiltonian. But in a simple model, a model ferromagnet, spin a half ferromagnet, that is the case. Then the total moment you get quantum mechanically like that. In an antiferromagnet, things are more complicated because the excitations are not good eigenstates of the Heisenberg Hamiltonian, for example. So here's what you get for a spin a half antiferromagnet, such as lanthanum cuprate, high temperature superconductor. This is the amount in the Bragg peak, and then the amount in the spin waves. And we know that you get other excitations called multimagnons as well. So there's the fact these exist is a consequence of these not being good eigenstates. Okay, so with that, I'll finish the lecture. Thank you very much.